All right, we're back again with chapters 12.1 and probably 12.2 as well. So we're going over the three-dimensional coordinate system, which, as you might have noticed, is one more than the two-dimensional coordinate system that you're no doubt used to. And then also a quick introduction to vectors. Just to get a sense of how this is going so far, did anybody watch the pre-class videos before? Oh, wow. Nice. That's more than four of you. Great job. Cool. So I may, depending on the day, I might go over a very quick summary of the pre-course videos at the beginning of a lecture, but mostly I'll try to just dive into the new stuff. But since it is the first day, and well, first day that counts, I guess, and there's more than four of you that didn't watch it, I'll quickly go through the beginning stuff. So again, we're jumping up to the three-dimensional coordinate system, which means we're going to add a z-axis to our usual x and y. So it makes space instead of a plane. Three dimensions are, it's like what we walk around in roughly. The most exciting part to talk about here, though, is the right-hand rule, which is how we order the x, y, and z axes, because that is going to be, like, order is going to matter for us. The most standard way to organize the axes is to have x coming out of the page, y going left and right, and z going up and down. That right-hand rule has a couple of different forms, the most common of which looks kind of like this. If you're watching the video, I'm terribly sorry, but you're not going to be able to see my hand right now. I suppose I could turn my camera on, but that's a lot of work. So just Google it if you're watching the video later. It'll pop up. But again, you just kind of stick your index finger straight up, your middle finger straight out, and your thumb in the only direction that your thumb wants to go. And that's going to, I don't know, you put that together with the x, the y, and the z axis. How does that thing work? Oh, wait, no, I'm doing scratch that. Let's go back to starting over from the right-hand rule. We're going to use one where we curl our fingers instead. There are two versions of the right-hand rule. Both can work, but I think the one where you curl your fingers is better. So if you want to know the order in which to place x, y, and z, start by taking your fingers, sticking them in the direction of the x-axis. From there, you'll want to curl your fingers in the direction of the y-axis. So starting from x, which is straight out, curl over into the y direction, so that your hands make a curl going around x and y in the counterclockwise direction. Your thumb is only going to be able to go one direction, and that's the way that z goes. So we can go order x, y, and z in any way we want, as long as we follow the right-hand rule. Or we can just stick to as much as we can, stick to our standard order for x, y, and z. Where again, x will be in and out of the page, y is left and right, z is up and down. I think up and right both make a lot of sense as the positive directions. So I don't think there's any need to go over that. You're used to that from X and Y. Right is positive and up is positive. When it comes to in and out of the page, or in and out of the plane, we'll define out as the positive direction, while in will be the negative direction. We have a bunch of octants now instead of quadrants because we split space up into 8 octants instead of a plane, which is just split into 4 quadrants. And nobody really has a great numbering system for the 8 quadrants or the 8 octants. The only one that we really decided on was the first, the one where all 3 directions are positive. That's the first octant. All of the others are just whatever octant you want to talk about, but they don't really get numbers. Excuse me. They don't really get numbers in the same way that the quadrants get numbered. Then there's some stuff about how to plot some points, but I'll leave that as an exercise. Let's jump into the during class section. Hey, no, don't do that. Well, it's going to be a great looking video. All right. 1.2, surfaces in space. What do we want to do? So after a quick introduction to our three-dimensional coordinate system, I want to just generate a few equations, except that these equations now are going to exist in 3 space. And I want to quickly check to see if a given point exists on that surface. So once we start talking about things, I'm getting a little ahead of myself. Let's just check to see if the point 1, 4 is on the line x minus 4y equals 1. And this, I am going to guess, is some review. Since you've done this in algebra, if I want to see if a point's on a line, I should just plug it in. So 1 minus 4 times 4 is equal to a number that I can probably do in my head. 1 minus 16, that's negative 15. I really hope. And notably, negative 15 is not equal to 1. Hopefully that math checks out. So I'm going to argue that point is not on that line. Okay, so we did back in algebra. When we step things up to our 3-dimensional coordinate system, we just plug that same point in, but now there are 3 variables instead of only 2. So this might look something like 1 minus 4 times 4. 4 times 4. Plus 8 times 2. So you may have already noticed the important bit about how we order points in 3 space, which is just we add z alphabetically to the end of our point system. Right, so our usual points back in the plane were x and y in that order. Now that we're going to add a z point, it's just the 3rd coordinate. So x, y, z. And one of the things that I'll just mention about my notes at the beginning is that I'll try my best to color code a few things to kind of help you follow your way through problems. One of the things I've tried to standardize is using specific colors for x, y, and z. This is just particular to me and my own notes. It's not a standard mathematical talent or anything like that. Just in my notes, I'll be using purple for x values, yellow for y values, and I think that's magenta for z values. I'll be somewhat consistent throughout that, or I'll be somewhat consistent with that throughout the semester, or, as much as I can be. But anyway, we've got a few numbers on the screen there that we ought to resolve. That looks to me like 1 minus 16 plus 16, which is equal to 1. And then that is notably equal to 1. So I'd say, yes, that thing is on the plane. X minus 4y plus 8z equals 1. More on how we know stuff is a plane later. For now, just take my word for it. That's a plane. One more time through, plug in 1, negative 3, 0 into that surface. Well, x, y, z is going to get multiplied by 0, since the z is 0. X squared is going to be 1 squared. And on the other side, I've got y, which is negative 3. And once again, 1 and negative 3 are not equal. So I'll say, no, that thing's not on the plane. I don't know why I went to orange instead of red. No. Cool. I think that about does it. So with some of those checks out of the way, why don't we take a stab at trying to graph some things? Starting with y equals 1. Very simple shape in our xy plane. So we're going to start graphing it there. And then we're going to get real exciting and try and graph that same equation, but in 3 space. So first things first, let's go give ourselves some coordinate axes. It'll be all right if that overwrites into the next problem. I have a straight edge, so I'll pull that out. Hey now, there we go. Here's our line, y equals 1. If I were to describe that shape in words as best as possible, I would probably say that it's a line. And probably a bit of review still. I'll label my coordinate axes because that's probably important, particularly when we step this thing back up to 3 space. But back when we had just planes, we usually did X as left and right, Y as up and down. When we go into 3 space, we're going to take that plane that usually is, kind of sitting in the page, and we're going to lay that flat so that now X is going to come out of the page, Y will go left and right, and Z goes up and down. So if I put a 3-dimensional coordinate system on here, hey, look at that. Bunch of axes. Go and label some of these. Y is going to be this axis. Z is the one that goes up and down. X comes in and out of the page. And I'm going to claim that Y equals 1 is about that point on the Y-axis. So if I want to sketch out what Y equals 1 looks like, well, let's see, what kind of an angle did we get here? 49-degree angle? Sure. Well, I think everything along that line is going to be at Y equals 1. None of my other variables are defined in the equation, so X and Z could be whatever we want them to be, which means if I just shift this up to be out instead of at the plane where Z is equal to 1, maybe move this up to where Z is equal to, I don't know, some other positive number. I think that this line is also Y equals 1. Just imagine that's been shifted straight up the Z axis. I think also if I were to move down, I'd also see maybe a line down below that also satisfies the equation Y equals 1. Same with anything along the x-axis. Maybe anything here and anything over here. I think all of those lines are going to satisfy the equation Y equals 1. Maybe for a moment, I'm just going to erase that first one I put down and kind of look at the resulting shape that's showing up there. And I think this is creating a plane, right? Where X and Z can be whatever we want them to be, just as long as the Y coordinate is 1, that equation is going to be satisfied. So if you imagine a set, any number of coordinate points that have 3 coordinates in them, as long as the middle one is 1, anything else will work. Any other spot in there works. So if I were to describe that as best as possible, I would say it's a plane. And also I have some computer generated planes over here on the right, which might be a little easier to look at rather than my stumbling through drawing a picture, even if I am using some decent tools to get that done. So glancing at those first two, I have the plane Z equals 3, one that's over on the left. That thing is going to be parallel to the XY plane, being the one that's we're laying flat, calling that like sort of our ground. Z equals 3 is just that plane, but shifted up to a Z coordinate of 3. Y equals 5 then is a plane in 3 space, where as long as the Y coordinate is 5, any other point that's in that blue plane is going to work. Specifically, I want to draw our attention to the equation Y equals 5 back in 2 space. So 2 space instead of 3 space, where Y equals 5 is just a line. If I'm going to step that up into 3 space, that equation evolves into a plane. Yeah, so that's I suppose what I should say about that. Moving back on, let's look at some more complicated shapes. And maybe if you're looking at the other shapes that I had over on the right, you might see where this example is going. I want to graph the equation x squared plus y squared equals 4 in the xy plane. So again, I'll bring out my xy plane. I'll label it again, x being that way, y being this way. And I know x squared plus y squared equals 4 is a circle with a radius of 2. That looks like a circle. And that's more or less centered at the origin. And I'm sort of freehanding these diagrams, so some of them are going to look better than others. But if I were to describe this in words as best as possible, I'd say it's a circle. And if I were to do it as best as possible, I would claim that its center is at 0, 0, and its radius is 2. Since the square root of 4 is 2, and our standard equation for a circle looks an awful lot like the Pythagorean theorem. So that other side is squared. If we were to take that same shape, with that same equation, x squared plus y squared equals 4, but this time graph it in 3 dimensions, what does that look like? Is a question I'm asking us and also plan on answering. Cool, some coordinate axes. Well, I know it should look at least kind of like a circle, since I was already using a circle when I was back in a plane. I could still see some sort of circular shape show up in 3 space. So if I try my best to draw that circle, how about that? And maybe move it slightly so it still looks sort of centered. If that's my same circle in the xy plane, again, labeling my x-axis right here, y-axis there, and z-axis being this guy going up and down. In the plane, or in the xy plane, I should see this same shape that I saw when I graphed it in 2 space. But now, since z is not defined, that same shape could exist in any plane where z is kind of whatever we want it to be. Right, so if I just take that circle and move it up the z-axis, I think I'm going to get the same shape that also satisfies the equation that was given. Maybe if I just kind of line up these, hey, I said line up these endpoints. Come on. There we go. I think that both of those circles, even though they look like ellipses, they're, supposed to be circles. We're just looking at it from a funny angle. I think that both of those circles are gonna work for the equation x squared plus y squared equals 4. So they're both circles with a radius of 4 and parallel to the xy plane. But since z isn't defined, it can be whatever we want it to be. So if I throw another one in, but maybe move that circle down, this is roughly the shape that I'm getting. I just kind of plot a few of those pieces in there. And hopefully that diagram is good enough. You can see this taking the shape of a cylinder. And a cylinder in the sense that we all know what a cylinder is. Looks like a soda can or a pop can, I guess. We are in the Midwest. So I'd claim, that thing looks like a cylinder. Again, kind of bringing things over, not to spoil that too much. Back to some of those computer-generated images. If we have the circle x squared plus y squared equals 1, with z equal to 3 specifically, we get a circle up where z is equal to 3. But if we don't hold on to that specific idea that z equals 3 and instead just say x squared plus y squared equals 1, probably shouldn't get too far away from my microphone, we get this cylinder, right? Circular base, and it just moves up the z-axis. When it comes to shapes in 3-space from a mathematical perspective, we're going to expand the idea of what a cylinder is. This is a very classical version of a cylinder. If I say cylinder, that's probably the shape that everybody conjures in their head. We're gonna play with that and make it a lot more complicated, but not today. That won't be until section 6. But just know that eventually cylinders aren't really going to be cylinders anymore. Well, they'll still contain cylinders. There will just be more kinds of cylinders to the point that they're almost not even recognizable. So we have that to look forward to. Yay. One more equation. Let's graph z equals y squared in 3-space. No, don't do the eraser. I just want you to give me the coordinate axes again. And if I want to draw the plan or the equation z equals y squared, it'll look an awful lot like y equals x squared. So if I'm just trying to stay in the x or the yz plane, put like z there, put y here, x down there. Again, we'll keep labeling our axes since it's particularly important today. Like in the yz plane, that's my equation z equals y squared. It's a parabolic shape like we're used to seeing from algebra. But now, since I'm in 3-space, I can mirror image that shape, but just move it down the x-axis. Put another one, but maybe move it into the back. So I might be seeing this sort of parabolic shape extending along the x-axis with, let me just match this angle again. Hey, look, a perfect 45. Or close enough to it. Sort of cross sections that move parallel to the x-axis. I don't know if this one's gonna still look good when I go through here. We'll find out in a minute. Maybe we draw one also along this outside edge too. Come on, there we go. So I think that almost kind of like a half pipe shape might be starting to present itself. Can't tell if that last line was helpful or not. But in a rough sketch, I think that that's what I'd come up with if I tried to draw it. So hopefully that looks good. We'll do our best to sketch some shapes out, but oftentimes it is nicer to look at some computer-generated images instead, because it'll be a lot easier to see what's going on. So a tool that I would strongly recommend you get familiar with is something on the internet, and it has a name that I totally remember. That's the one. Thanks. Yeah, Monroe CalcPlot 3D, right? CalcPlot 3D. Google this. If you do that, it should be the first hit that pops up. It's just a 3D graphing software that works in a browser. You can type your equations in. If you watched the pre-class video, which I know that more than 4 of us did, you would have seen what the thing looks like. It'll let you generate a 3D image, and then you kind of drag it around and rotate it. It helps a lot with visualization, which is a particularly important element of what we'll be doing in multivariable throughout the semester. Oh, and right, there's the section on spheres. We've got, what, 25 minutes? Yeah, we should still have enough time to get through everything. So, talking about spheres. They've got an equation that is going to look pretty familiar to us. So we want to look at the distance formula in 3 dimensions. As a quick reminder, back in 2-space, the distance formula was the difference in x values, so x2 minus x1 squared, plus the difference in the y values squared. So our distance formula really just is the Pythagorean theorem, where x is the horizontal distance, y is the vertical distance. That creates a right triangle. Pythagorean theorem says square the two legs, add them together, you get the square of the hypotenuse. And that's the distance formula. The same thing, pretty much, works in 3-space, where we're just going to add a third term to our Pythagorean theorem, if that made any sense at all. So we're going to still use x2 minus x1 squared. We'll also add y2 minus y1 squared. And if you're particularly clairvoyant, you might know we're going to add z2 minus z1 squared. And that is just a natural extension of the Pythagorean theorem to work in 3-space. We can still create a right triangle, or maybe a series of a couple of right triangles that'll get us to our hypotenuse, being the thing that goes from the origin out to our point, or rather, the hypotenuse is the length between those 2 points. Oftentimes it's going to end up being the origin. But for this generic form, just for any 2 points out in space. And again, yeah, it's just the Pythagorean theorem, but now with extra steps. Yay. Might as well do one example over here. Calculating the distance between these 2 points. That's going to look like 1 minus 3 squared plus 2 minus negative 1. I'm going to call that 2 plus 1 squared plus 3 minus 0 squared. And all together, that looks like negative 2 squared is 4, plus 3 squared is 9, plus 3 squared again is also 9. Unless I'm very much mistaken, that's the square root of 22. The square root of 22. Is my pen running out of ink? It's an electronic pen. It shouldn't be able to do that. And just like we did back in 2-space, where we upgraded our Pythagorean theorem to instead just be the distance between 2 points, to be the set of all points that are a fixed distance away from some center point, which gave us a circle. If we upgrade that idea to 3-space, we get a sphere. So circles sort of have 2 natural extensions when we go to 3-space. They can either naturally extend into a cylinder or into a sphere. We're going to do a lot more with looking at cylinders and spheres when we move into our special coordinate systems. Again, that's looking ahead. So we did cylinders back in section 1.2, the stuff that we just did, 10 minutes ago. Here we're looking at spheres. So the equation of a sphere, which we're going to keep filling in these notes, with a center at HKL and a radius of R, looks an awful lot like the equation of a circle with a center of H and K and a radius of R. We're just going to add one extra element. So we'll have x minus h squared plus y minus k squared, which are the 2 terms that show up in the equation of a circle. To make that thing a sphere, we'll add z minus l squared, all still equal to the square of our radius. So that'll be a sphere, right? Just add in that extra z term, that extra z squared term, and we upgrade a circle into a sphere. So if we wanted an equation of a sphere with a radius of 2 centered at that point, it should look something like x minus 1 squared plus y minus -2, also known as y plus 2 squared, plus z minus 3 squared. And that's equal to 2 squared, which I believe is 4. Even I can do those numbers. Yeah. And likely you just want to leave your equation like that. Could FOIL it out if you really wanted to. I wouldn't stop you, but I would maybe recommend that you leave it just like that. Be a lot easier that way. I feel like I had another bit pulled over to the side for this part. Yeah. Just brought in the equations of the sphere and the distance formula in 3 space to be typed out, grabbing that from the textbook. But yeah, enough on that. Let's go look at the harder problem. Or rather, the easy one first, then we get a harder one. Describing the surface, x squared plus y squared plus z squared equals 1 as best as possible. This is the unit sphere. Unit sphere. If that sounds familiar, it's probably because you're remembering the unit circle, which is a circle centered at the origin with a radius of 1. So the unit sphere is a sphere centered at the origin with a radius of 1. So center at 0, 0, and a radius of 1. If we wanted to take that idea but make it even more exciting, here's an equation that's also going to end up being a circle but doesn't look like it at first glance because it's got everything foiled out. So if I were to try to describe this thing as best as possible, that means I want to identify it as a circle, which means getting it into a form where I can recognize it as a circle. And maybe you can pick that out from its expanded form. I think general form is the name that this thing gets. But we'll also want to be able to read a center and a radius off of this guy. So here's what I would do. I am going to break this equation apart into 3 pieces. So that I have an x part, a y part, and a z part. Just group those variables in each of their own separate categories, and then just work on one variable at a time, which is going to be a fairly common practice throughout the course. Since we have multiple variables that we have to deal with in one problem, we often find it's easy to just work with one of them at a time. Usually if we can figure out what one variable is doing, and then the next, and then the third, then we can put those 3 ideas together to see what the whole shape is doing. But yeah, pretty common practice is to take a complicated problem and break it down into simpler steps. So let's do that. I've got over here x squared minus 2x. And the thing that I want to do is put the circle back into factored form, which means I want to complete the square. So that's what we're going to be doing. As you might recall from forever and ever ago, if I wanted to have a complete square or do a complete square factor on x squared minus 2x, I want to add half of 2 squared, which would be 1. Now x squared minus 2x plus 1 factors 2x minus 1 squared. X minus 1 squared, which is what I want to be doing. I'll do that same process for y. But there's not really much to do. There's only a single y term. So I don't need to add anything, but I'm still going to add a plus 0 in there just for fun. So this is going to be y minus 0 squared. But I do want to emphasize that I would be completing the square here if I had to. So I'm just going to add that into the notes. Do that process one more time. Because again, 3 variables, so we'll do it 3 times. I don't want to work in that line just yet. I have z squared plus 4z. And if I want to complete that square, half of 4 is 2, and 2 squared is 4 again. So I'm going to add 4 right there. I now have a perfect square trinomial for the z variable, meaning that I can do the thing where I factor that, call it z plus 4 squared. And then I just need to balance my equation. Because so far I just added the numbers in there because I wanted to. It seemed like a good idea at the time. And I'm going to argue that it was a good idea at the time. But in order to keep my equation balanced, anything I added to the left side, I should also add to the right side. So I'll add that 1 and the 0 and the 4. And 4 plus 1 plus 0 plus 4 is 9. And now in that second written line, I have an equation that I recognize as a sphere. So that thing has a center of 1, 0, -4. Remember that the correct version of the equation is going to be minus the center. So that sign's got to flip. And I see a couple of hands, which means I probably screwed something up. What's up? It very much is supposed to be z plus 2. Yep, I could tell as soon as a hand went up. I'm like, I definitely have screwed a number up. Yeah. Classically, canonically, I'm not very good with numbers. So that might happen a fair amount over the course of the semester. I usually get the letters right, but the numbers, well, you'll see. Yeah, that's definitely z plus 2 squared. Yeah, good catch. Oh yeah, so our center is definitely at 1, 0, -2. And our radius, I can spell radius. It's 3. So that's the square root of 9. It is still, I did still add up the right side, correct, didn't I? Radius of 9, square root of that is 3. Is it supposed to be 2 instead? I don't think so. No? All right, cool. So yeah, as soon as I make that first mistake, I lose all confidence in what I'm doing up here. But yeah, I'm pretty sure I still get 3. All right, and with another 10 minutes, let's do a lightning speed run through the next set of notes. Because we do want to cover a couple of things today. So an introduction to vectors that I would have loved to have left myself more time for, which might mean I'll just cover it again at the beginning of Friday's class. So vectors, kind of a big important element of Calc 3. So vectors are defined as a quantity that has both magnitude and direction. So I think the easiest way to understand the difference between a vector versus just a number, as far as trying to like interpret this in the real world instead of in a mathematical sense, is the difference between speed and velocity. Guessing most of you have seen at least some physics, so I bet you know those two words. If you're in your car and driving down the highway, your speedometer will tell you how fast you're going. But if you're only looking at your speedometer, while you'll know how fast you're going, you wouldn't know where you're going other than just down the highway. So the thing that takes the scalar value of a speed and turns it into a vector is adding a direction to that. So if I'm driving from here to Detroit down 96, then I would be traveling at, let's go with 77 miles an hour east. And now that's a vector value because I've got both a magnitude, 77 miles an hour, and a direction, east. Directions can be as simple as just cardinal direction, north, south, east, or west. Or as we'll see in our coordinate planes, our coordinate spaces, directions can be any direction that we can think of in space. And so again, we'll want to use some vectors to represent that stuff. We can calculate magnitudes of vectors or lengths of vectors. Length and magnitude are going to be interchangeable for at least a while. I actually don't remember if we're going to bother defining length and magnitude differently. Let's just go with length and magnitude. We're going to use those interchangeably until I think of a reason not to. Right, so the lengths or magnitudes of these vectors are still just the Pythagorean theorem. Nothing much has changed there. And we claim that two vectors are equal to each other as long as they have the same magnitude and direction, which notably means that I can have vectors in two different places that are still equivalent to each other. So these two vectors, v and u, the one in blue and the one in green, are the same vector, even though they're not located in the same spot. The vectors are independent of position, or at least position in the 3D space. The only thing that matters is just how long they are and the direction that they're going in. So if two vectors are parallel and they have the same length, we consider them equal even if they aren't overlapping in the diagram. Now the lines that those two vectors on are of course different, but the vectors themselves, again, we consider them to be equal to each other. So we have the thing called the position vector, which if I take any point in space, the position vector to that point is just the vector that goes from the origin to it. Here are some position vectors versus just other vectors that are out there. If I wanted, say, to look at this third example, the position vector to point A out there, which is at -1, 4, -5, is just the vector that goes from the origin to -1, 4, -5. A rather important element about vectors that I probably should have said in the last example is that they're all directed, right? Because they have directions, right? Is important. The vector has both magnitude and direction. So unlike lines, which are just plotted on some sort of graph, and it is a line, a vector needs to have an arrow drawn on it somewhere. So vectors go in whatever direction is signified. If I look at, say my vector here is v, if I look at -v, so if I just slap a negative at the front of my vector, that reverses its direction. So it'll again be, the same line. So if I'm looking at, kind of this line that I'm highlighting on the screen right now, v moves roughly to the upper left. If I looked at -v instead, it would move to the lower right. Right, so the negative of a vector will simply reverse its direction. And do I have enough examples of the ways that we write vectors on here? Yeah, okay, here's one. So when it comes to how we write vectors, if it's a computer writing it out, we often use bold to indicate that a value is a vector instead of a scalar. So what color do I want to use here? How about orange? Bold. Bold means vector. Of course, if I'm just writing with my pen or pencil, depending on what the case may be, it's rather hard to just handwrite in bold. So we'll be more specific about labeling something with a vector on paper by giving our variable names these little hats. So if I want to signify that something is a vector and I want to be extra clear about it, I'm going to put a hat on it. like we have right here. Kind of looks like a little vector sitting on top of the letter. And we'll use that to indicate that something's a vector. Now, I've thrown around the word scalar a couple of times, but I haven't really bothered to define it. So I should probably do that. A scalar is just a number, like 7 or 12 or pi or 53 or -17. All of those are just numbers, and to very specifically delineate them against being a vector, we call them a scalar. So just regular old numbers are scalars. When I talk about the difference between speed and velocity, speed being just the number that you see on your speedometer, speed is a scalar because it doesn't have any direction associated with it. Whereas vectors are numbers that also have a direction. So when I want to be very specific about when I'm talking about what is a vector and what isn't a vector, I call vectors vectors, and the things that aren't vectors, scalars. Or at least the numbers that aren't vectors, scalars. I suppose there are a lot of other things out there. But yeah, scalars and vectors, we'll use those quite a lot throughout the course. So I'll do my best to be specific about when I'm talking about one thing or another. We'll also use the word vector valued function a fair amount. And all that means is that the function I am referring to expects to have vectors as maybe its input or its output instead of just a number. Cool. So another way that we write vectors out, let's look at this example right here. I've got a couple of vectors here in 3 space, A and B. So A is the vector 1, 3, which just means it is the vector that goes from the origin to the point 1, 3, just points in that direction. We use these angled brackets to represent something as a vector, as opposed to parentheses when we want to refer to something as a point. But points and vectors are going to look pretty similar to each other. Because they are kind of the same thing, right? Because the position vector just is a point, but with angle brackets on it instead of parentheses. And fortunately, I did most of those examples because I need to jump ahead to the last super important topic that I just barely covered in time. So the standard basis vectors. Are I, J, and K. Zero, one, zero, and K, which is 0, 0, 1. I very quickly glossed over all the unit vectors, but we'll see plenty more of that, especially on Friday. But the standard base vectors are going to show up a fair amount. All they do is they just represent an increment in each of the x, y, and z directions respectively, I, j, and k, x, y, and z. So that another way to write out a vector, and I know I'm basically out of time, so just one example here real quick. The vector 5, 2, -4 is the same as 5i plus 2j minus 4k. Cool. So those are the basis vectors. I'll pick up there on Friday. Okay, bye, 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 bye. All right.